Welcome everyone to Power Electronics and Embedded Systems webinar. My name is Erica Reed, and I am the Program and Marketing Manager for the MSCE on Coursera program at the University of Colorado Boulder. It gives me great pleasure to introduce our special guests. We have Professor Bob Erickson. He's the creator of Power Electronics Specialization, Power Electronics Project Course, and Photovoltaic Power Electronics Specialization. Next, we have Professor Tim Scherr, creator of the FPGA Design Specialization. And finally, we have Professor Dan Walkus, creator of the Advanced Embedded Linux Development Specialization. Now, before we get started, let's familiarize ourselves with the Zoom interface. To use the Q&A, hover your mouse towards the bottom of your screen, then click on the Q&A icon to type in your questions. Please do not use the chat function. We will address your questions at the end of the presentation during the Q&A session. Now, this webinar will give an overview of Power Electronics Graduate Certificate, Embedded Systems, Industrial Internet of Things Graduate Certificate, FPGA Design, Advanced Embedded Linux Development, and a brief overview of the MSCE on Coursera program, followed by Q&A. Now, with no further ado, I turn this over to Professor Bob Erickson to start us off with Power Electronics.
Okay, thank you, Erica. Yes, I'm a professor of electrical engineering at the University of Colorado Boulder. I wrote the textbook, Fundamentals of Power Electronics, which we use in a number of our classes, both on Coursera and on campus, and that is used in other power electronics programs around the world as well. I've taught power electronics using Coursera in various ways for the past 10 years. I've been a big fan of using Coursera this way because it enables us to really offer a lot of material to continuing education students in ways that would just not be possible if we stuck to the traditional live semester on-campus format. So I'll talk briefly about what is power electronics. It's been estimated that by 2030, nearly all of the nation's electrical power will be processed, converted, and controlled by power electronics. Some applications, are, I guess, traditional applications such as cell phones and laptop computers. Renewable energy applications such as solar and wind power, electric vehicles where the power electronics is in the heart of the propulsion system and the charging system of electric vehicles, and other new applications that are just growing exponentially today. And what we need is high efficiency, sophisticated and accurate control, and small size and weight of the power electronics. And we offer a detailed curriculum in these areas. So Erica, the next slide, please. So in power electronics, the heart of the power electronics is what we call a switching converter that processes electrical power, and it can convert it from one form to another, such as DC to DC, DC to AC, or any of the different combinations. And it can change and control the magnitude and the frequency. So we have DC-DC conversion, where we're changing the voltage, AC to DC rectification, such as for charging a battery, where we control the charging rate of the battery, DC to AC inversion, where, for example, we take DC from a battery and produce variable voltage, variable frequency AC to drive a motor, and AC to AC cycloconversion, where we may change the frequency and the voltage. We think of the switching converter, this analog box, as being, in some sense, the brain of the power system. It's controlling and performing the functions needed in the application. And the switching converter then has to operate with high efficiency and have small size and weight in most applications. Next slide, please. Control is always needed. And what we need to do is usually control, say, an AC or a DC quantity according to what the application requirements. So in fact, besides the analog circuitry and the switching converter, we'll have digital circuitry that does this control function that is in fact an embedded system. So we have sophisticated digital control in addition to the analog functionality. Next slide, please. Okay, here's a few applications then. The electric vehicle is a very popular application area today, and there's a big need for power electronics engineers working in this area. The power electronics is, first of all, in the core of the powertrain, where it takes the DC of the battery system and produces variable AC as required to control the speed of the electric motors that propel the wheels. Also, charging the battery is an important function. And so we have battery chargers that interface to the AC grid and control the charging of the battery. Next slide. Hybrid vehicles are also important, and they have similar but smaller power electronics in them. So again, we have power electronics to both receive energy from the battery pack or from the gasoline engine and produce AC as needed to drive the electric machines that propel the car. Next slide. Wind turbines have been an important application of power electronics. In a variable speed wind turbine, the speed at which the wind turbine turns depends on the wind speed. And as the wind goes up and down in speed, the wind turbine will operate at different rotational frequencies. And then the AC generator that is converting the mechanical power into electrical power will produce variable frequency and variable voltage AC. And then we need power electronics to convert that wild AC into fixed 60 hertz, fixed voltage AC to interface to the grid. Okay, next slide. Computer power supply systems have always been economically very important application. And today, a cell phone or an iPad or a laptop computer is full of all kinds of power electronics. So we'll have a battery, say a lithium battery inside a cell phone or a laptop. We'll have DC to DC converters that produce variable or various DC voltages as needed by the systems in the cell phone or laptop. We'll also have a charger that can charge the battery from the AC power line, and we have management of the battery state of charge to try to improve the life between charges. So today, a cell phone will have a lot of embedded systems type circuitry, and it'll have a lot of power electronic circuitry. Okay, next slide. We offer a number of courses in power electronics, and you can go to our department website to see which ones are offered via Coursera. In the center of these is a graduate certificate that is issued by the campus graduate school, and it consists of 9 credit hours of Coursera-based 4-credit courses that are listed here. There's a specialization that's just called power electronics that is the basic power electronics material that we offer, and I teach that course out of my textbook. We have a second, more advanced course in more advanced modeling and control of power electronics that is offered, or the instructor for that is Professor Maximovich. And then we have a project course to finish up the graduate certificate. The project course is a 6-week design project that I'll talk about in a minute. Okay, next slide. Here's a coursework example, the very first introductory course in the basics of power electronics specialization. It's a 4-week course. It has 3 homework assignments plus a final exam. The first assignment is a basic LT-SPICE simulation of a boost converter. The second one is a written homework assignment on analysis and design of a buck boost converter. The third one has some more detailed modeling of efficiency and losses with 2 different applications. And then there's a final exam. So it's a 4-week course. Okay, next slide. The capstone design course involves design and then design verification of a DC-DC converter to be used for USB Type-C power source. So it involves both design of the power stage and the analog electronics, and then verification that the design works and meets requirements using LT-SPICE simulation. Then there's design of the controller circuitry and verification of that controller circuitry. The milestones involve really submitting reports and the simulation files that prove that you meet the rubrics that are very well defined. And after you submit your design, then you'll get 2 other students' designs to do peer grading, which is very straightforward. What you do is you simply verify that they did indeed meet the milestones or meet the rubrics that are really tested simply by the LT-SPICE program automatically. Okay, this has been a popular course that really culminates the certificate. Okay, that's my summary of power electronics. Now I'd like to hand it over to Professor Scherr to discuss embedded systems.
Thank you, Professor Erickson. I am Tim Scherr. I'm an associate teaching professor at the University of Colorado. Prior to this, I spent over 30 years in various industries as a design engineer and engineering manager, and it's my privilege to pass on the lessons learned from all that experience in embedded systems design. So I'm here to describe our offering in embedded systems design, which is a very dynamic and exciting area in the field of electronics. And so first, I want to talk a little bit about what are embedded systems. So if we go to the next slide. An embedded system is a computer system that's dedicated to one primary function as opposed to a general purpose computer system like a laptop or something like that. And usually this dedicated computer system's inside of a larger system. So some examples where you might find embedded systems include industrial automation, home automation, medical devices, consumer products, and transportation. So as the picture shows of the automobile there, a typical automobile might have 60 microcontrollers in it, and each one of those is the heart of an embedded system. Next slide. So then what is an embedded systems engineer? Not just a software engineer or a programmer, and it's not just a hardware circuit designer. The embedded systems engineer combines these skills with systems design knowledge to architect and build embedded systems. Next slide. So our embedded systems engineering courses are very hands-on. Most will require the purchase of development kits like the ones that are shown here, at least for the final capstone course. You may be able to go to some of the initial courses without having to purchase hardware. The DE10 Lite board at the top here is used in the FPGA specialization. And in the lower right corner is the Cypress PSOC evaluation board, which is used in the embedded sensors and motors specialization. So this is just kind of an example of the type of boards that we might use as part of the courses that we offer. Next slide. So embedded systems engineers are employed by profitable high growth industries as shown in this table, which shows the Internet of Things technology markets. Our graduates have obtained positions at a lot of major companies like Apple, Intel, Cisco, Qualcomm, and others. And there continues to be a really large demand for engineers who can design embedded systems. Next slide. So to address the needs of industry in the Internet of Things, we offer this Industrial Internet of Things graduate certificate. It includes 3 specializations. First, the development or developing the Industrial Internet of Things, which describes the whole business of creating small computer systems that go inside of machines and maybe talk machine to machine and so on. The second specialization is embedded interface design, which uses Python and other computer languages to create interfaces from machine to machine. And then the last specialization is embedded sensors and motors, which of course talks about how to do motor control, how to interface to sensors, and so on. The topics shown here have enabled students that finish this certificate to advance their careers in the IoT space. We have syllabuses listed on our website. Carly will put the link in the chat that provides the course syllabuses for embedded systems courses. All right, next slide. We also include a set of courses with more of a hardware emphasis, FPGA Design for Embedded Systems. FPGAs, or field programmable gate arrays, are the core parts in a lot of digital electronics designs. They allow customization of hardware, which is more important perhaps in embedded systems than it is in more general purpose systems. And it too is a very exciting and dynamic field to be in at this point. The courses in the FPGA specialization are Introduction to FPGA Design for Embedded Systems, in which development tools are introduced and used to build a sample project. That sample project will be peer graded, and then there are other assessments that are done that are auto-graded within this course. The second course in the specialization is Hardware Description Languages for FPGA Design. In this course, students learn the art of describing circuits using VHDL and Verilog code, so a couple of hardware description languages that are used in FPGA design commonly. The third course in the specializations, FPGA soft processors and IP acquisition. In this course, students learn to build soft processors in hardware and then program it in software. And then the last course is a capstone course called Building FPGA Projects. This gives the students the opportunity to build a complete FPGA system using real FPGA hardware based on the Intel Altera Max 10 FPGA and the DE10 Lite, which is the board that was shown earlier. All right, next slide. So here are some examples of what you might see as you're working in the courses in the FPGA design specialization that I've created. An introduction to FPGA design, it begins by working through an example project. First, digital logic design is reviewed and then reoriented to programmable logic, which is mostly implemented in lookup tables. From this background, a sample project is done using the Intel Altera development tool that's known as Quartus. So this is all done in your PC in software. We use this tool then to create a pipelined multiplier circuit, and then add additional circuits to this design. And there's kind of a schematic in the upper right corner here of this slide that shows what it looks like when it's being developed inside of the tool. The design then is verified by simulation and a static timing analyzer. The simulation waveforms are shown kind of in the bottom right of this slide. So in this course, as well as the next two courses in the specialization, no hardware is needed. We use the software tool with the design entry and the simulation as shown here in order to complete and verify the designs. So next slide. So then at the end of the specialization, we have a capstone course, which has the students building FPGA projects using the DE10 Lite FPGA board, which is shown here with one of the projects running. An entire system, as shown as in the block diagram here, is constructed and tested in the actual FPGA. At this point, the student has enough knowledge to continue to learn and develop their skill in FPGA design, and to probably get a job doing this kind of work if it's something that they're interested in. So to continue our discussion about advanced embedded system design, I am now going to turn things over to Professor Watkins.
Thank you. Thank you, Professor Scherr. And thanks everyone for joining. It's great to be a part of this. So my name is Dan Walkus. I have a background in electrical engineering, and I actually did my MSEE at CU in the early 2000s in the embedded systems group at the time, which is a small portion of what it is today. So it's great to be back and to be a part of the group here and speaking with you today. One of the original reasons that drew me to the program at CU specifically was the connection to industry. So I knew that I wanted to go back and work in industry. And I really liked the connection in industry in terms of professors who had some experience working in industry, a lot of them still working in industry full time. And almost a little over 20 years later, it's great to be back here myself. So I've spent around 20 years in industry, still work in industry, full-time developing embedded systems. And the last 15 or so years have been primarily developing systems which use Linux. In 2019, I took a part-time gig at CU, teaching with the same embedded systems group. And that summer, I worked to put together a course called Advanced Embedded Software Development, which is the basis of the Coursera course sequence that's available now as a part of the online MSEE. So I really I had some ideas about what I wanted to include in the course based on my Linux experience. It's really a lot of content that I had mostly picked up on my own over the years, or working with other teams of people who have had experience. But things that would have been great to cover in my graduate school experience, and in many cases, things that weren't yet available when I did my graduate degree. So I try to keep the content relevant and recent and cover a lot of current topics in embedded system development. So this slide talks about some of the reasons that you might want to spend your time studying to Linux. This is based on a 2019 embedded markets study where users responded to say if they were building embedded systems, what operating systems were those embedded systems using? And what you can see here is that there's a significant percentage of embedded systems that either use Linux directly or use something that's based on Linux. And in addition to the embedded systems which actually run Linux as a part of their OS, in a lot of cases, you'll find that the development of software for embedded systems is going to leverage Linux either maybe as a part of the build environment, maybe as a part of some of the testing or test automation. And so in general, if you plan to make a career out of software for embedded systems, Linux is probably spending the time to learn Linux is probably a very good use of your time. Next slide, please. So the Advanced Embedded Linux Development course sequence consists of 3 courses. The first one is Linux System Programming and Introduction to Builder. And in this course, we focus on user space applications. So the kind of applications that you would interact with directly. We'll develop user space software and build images using a build system called Builder that allows us to customize exactly what we want in our embedded system image and build an image that's suitable for deploying on hardware. In the second course of the sequence, we cover kernel programming and introduction to Yocto. So Yocto is a second build environment that you can use for building embedded systems images and customizing the content of the images. And the Linux kernel software development portion is going to cover things like building a custom Linux driver and some of the different programming constraints we have when we're dealing with kernel development. It'll also talk about the interaction between user and kernel space and help give you an idea about what's happening under the hood when the user and the kernel space interact in your software application. The third course in the sequence is Linux Embedded System Topics and Projects. And this is the capstone course where you take the knowledge that you learned in the first 2 courses and create a custom project that will run on hardware. Next slide, please. So in terms of the overview of the coursework covered in the Advanced Embedded Linux sequence, there are a total of 9 structured assignments. So these are across the first 2 courses in the sequence. The first through the 5th assignment focus on user space programming and building images using Builder. The 6th through 9th cover the kernel programming aspects and building images using Yocto. And the first 9 assignments are all able to be built without any dedicated hardware. The only requirement is a build machine, typically like an x86 laptop or some type of embedded host host you can use for your build system. The final capstone custom project is deployed to a embedded target of your choice. So with the first 9 assignments, we'll build on the host and we'll target an emulator and emulated hardware. With the capstone custom project, you migrate your project work that you've done in the previous semester or the previous portions to focus on a specific hardware platform, and you'll deploy to hardware. There are a couple different hardware examples available and some resources available to get you started on hardware deployment and targets some common platforms, including BeagleBone Black and Raspberry Pi. And you have the option to complete the custom project either on your own or in a group. And with the custom project, we'll track the work that we do with that project using Agile Scrum methodology and separate the development into sprints that track the work you've done toward the goal of your final project implementation. Next slide, please. So it's been a great experience and a lot of fun to watch what students have been able to come up with in the course of my time teaching at CU. And Carly's shared in the chat a link to the course page from CU where you can see the previous semester completed projects from students. So it's been great to see a lot of what we try to cover in the course is learning how to leverage a lot of the open source projects that are available. And there's a lot of great projects that you can build on for your final project, a lot of examples of completed student projects that give you some ideas about what you can do. And just going over a few of the ones that have been completed in my on-campus course previously. On the left side, you can see there are 3 Raspberry Pi systems, one of them running some router software and communicating with each other via sockets. So transferring an image from a camera onto a 16:16 RGB matrix. And in the center, there's 2 different Raspberry Pi boards that are performing facial recognition using OpenCV and then serving up results on a web page and also pushing the resultant image stream up to the cloud. And on the right, there are 2 different Raspberry Pi boards streaming camera to a display in one case and interacting with a mobile phone over a Bluetooth BLE connection. So I'll now turn it over to Erica, who's going to provide more information about the MSEE program.
Thank you, Professor Dan Walkus, and thank you, Professor Tim Scherr and Professor Bob Erickson. That was very insightful. I am going to talk briefly about the MSE on Coursera program and how it differs from the traditional school system. A traditional on-campus graduate program requires an application process. Our program is performance-based admission, so no application required, which means no GRE scores, no TOEFL, no IELTS, and no letters of recommendation. All you need to do is to prove that you can do the work by completing a series of courses in what we call a pathway specialization with a cumulative GPA of 3.0 or higher, which is a B average. And that qualifies you to be admitted in the program as a graduate student at the University of Colorado Boulder. Now, each course in a traditional program consists of 3 to 5 credit hours. In our program, each course consists of bite-sized 0.6 to 1.2 credit hours. In order to get admitted, you will need to complete a series of courses. And each pathway specialization consists of 3 to 5 courses, which is equivalent to 1 traditional 3 credit hours on campus. In a traditional program, there are normally 3 semesters per year. Each semester is about 16 weeks long. Now, our program, and it runs 6 sessions per year, which is 8 weeks long. And traditionally, students pay per semester, which can be quite expensive because you have to pay up front. Conversely, in this program, you pay as you go, and the tuition rate is $667 per credit hour. Now, what will admitted students receive? First, students in the MSE on Coursera program earn the same credentials as our on-campus students. There are no designations on the transcript, certificate, or diploma to indicate that this is an online program. The students will have earned fully accredited Master of Science in Electrical Engineering or graduate certificate. And in addition, students who have been admitted in the degree program will receive a lifelong access to Handshake, which is a career-seeking tool offered through CU Boulder Career Services. Handshake is a place where employers post jobs as well as serving as a social network to connect with fellow alumni, including weekly virtual employer events. And finally, CU Boulder Graduate School policies apply to admitted students. These policies include course repetition, grade replacement, academic standing, and so on and so forth. So overall, by reducing the time commitment and the number of credit hours per course, students can earn the same rigorous degree or graduate certificate without the intensive 16-week commitment that traditional programs require. And these features allow for more flexibility in regards to time and finances, which is perfect for working professionals who may not be able to commit to a heavy workload over a 16-week period. And to learn more about our program, you can visit our website, which Carly has put on the chat. Thank you, Carly. And that sums up our power electronics and embedded systems presentation. We are now ready for Q&A, and Carly will be our reader.
Great, thanks, Erica. Well, thank you to all of our participants. We've received some really great questions in the Q&A feature. Professors, are you ready? I think we'll get started. So my first question is going to be for all 3 of you here, and anyone's welcome to answer it. Are your courses comparable to the on-campus version? And would you say the content is harder or easier?
Yes, we teach the material at the same level as the traditional on-campus graduate courses. So they're not dumbed down. The homework is machine graded for the most part. There are different types of grading. So the homework is in some ways different, but it's at the same level. So it's not turned up nor turned down, but it's real homework. Yeah.
I would say that. Go ahead, Dan.
Yeah, I would say the same thing for my course. The only thing I would add is that the on-campus course is sometimes more collaborative in terms of working with your peers. So balancing that with the more strict deadlines and like time to complete, you've got a little bit more flexibility in terms of deadlines and time to complete online, but it is the same content.
Yeah, I was going to say for embedded systems, I think everything that Professor Erickson said still applies. It's essentially the same content. There might be some differences. I know that when I prepare my courses, some of the slides that are used in the presentations are a little more clear than they are maybe on the on-campus version, because there isn't as much of an opportunity to ask questions. So we try to really polish those well so that the content's very clear that you receive when you take the course online. And some of the homework assignments are almost identical to what we have on campus. They are auto-graded online, and we actually have started to use some of the auto-graders in the on-campus setting as well. So the differences, are pretty small at this point between the two offerings.
Great, thanks. All right, to our panelists, our next question here. What materials or prerequisite courses would you recommend to someone interested in the program coming from a background in a different engineering specialty?
Yeah, we assume an undergraduate in electrical engineering, but you don't have to have that. Really, all you have to do is demonstrate you can do the work. Generally, you should have had calculus as an undergraduate. So if you're an engineer, you probably did. For the power electronics courses, we assume the students have taken our undergraduate circuits and electronics courses that are just the basic sophomore core courses. Yeah. So if you have that, then you should be okay. And if you don't have that, I would suggest there are, there's non-credit courses and circuits available on Coursera from other universities that could fill in material, any gaps. But, the way to really tell is to just try out the non-credit version and see how it goes. And then if it goes well, then you can easily upgrade to the 4-credit.
So for the FPGA design course, we assume that you've had a class in digital logic design and also some C programming. And that's really the only prerequisite for that course. And the other embedded courses will have similar kinds of assumptions about what it is that you already know. The syllabuses have really lengthy list of resources for studying in preparation or for enrichment once you've even completed the course. And so you can make use of those resources if you're trying to get ready to take a course online like this.
Yeah, I think the main thing for the Linux course would be C programming experience and having a bit of background in revision control, especially Git, would be great as well. But I agree that these are things you can also pick up through non-credit resources if you don't have that.
Great, thanks. So I'm going to target a few of you individually here with some specialized questions for each of your areas. So first, I'm going to start off with Professor Erickson here. What are the methods of electrical circuit analysis in the time system? What are the methods used in the frequency system?
Yes, well, in the time domain, it's pretty basic calculus. Really, it's just, can you integrate, say, a capacitor current to find the capacitor voltage, that kind of thing. And in the frequency domain, yes, we use the Laplace transform and phasor analysis, which is, sophomore circuits to write transfer functions. And we'll use those in designing control loops. We don't assume prerequisite knowledge of control systems. Certainly that doesn't hurt, but we teach what's needed in the course. So yeah, if you've seen a Laplace transform or seen phasor analysis before, then that's helpful.
Great, thanks so much. For Professor Scherr, what is the emphasis? Oh, excuse me, let me start that one over. Is the emphasis on VHDL or Verilog language for the FPGA courses?
So we actually have you learn both of them. So initial assignments will say, design an adder using VHDL, or maybe next time we'll say design a comparator using Verilog, and so on. So there's not, we're pretty agnostic. There's no favorite here between those two, and we try to take you through the fundamentals of both languages. When we get later in the course, when we have some more advanced problems in hardware design, we let you choose which one you're most familiar with. And so you can develop some expertise, more so on one language than another if you want to do that. But we try to support education in both languages as we go through the course.
Great, thanks. And to Professor Walkies, what is the best language to learn for embedded systems that complements a focus on Linux? Is that C, C++, Python, or other?
That's a great question. And I think if I have to pick out of that, I would definitely pick C, just for the main reason that the Linux kernel portion of the course, C is really the only option for developing Linux kernel drivers. Certainly all three of those are useful. And maybe if you've been following the notes about Rust in the Linux kernel, maybe 5 or 10 years from now, we'll have a Rust specific Linux kernel section, but right now it's all C.
Great, thanks. I have another question for all three of you. I'm going to start with Professor Erickson first. So what would you recommend to someone who already has an undergraduate degree in electrical engineering and is still figuring out whether to focus on power electronics or embedded systems?
Well, you can just go for it. I mean, I don't think you can go wrong. The degree lets you mix courses from different areas. So you could, and frankly, if you chose power electronics, it won't hurt you to know some embedded systems, because we have, microcontrollers controlling our power electronics. And so I think there's no wrong answer. I'd say take some embedded systems and take some power electronics and go from there.
Great, thanks. Professor Scherr or Professor Walkies, any other comments to add on that?
I would say that these are both areas in industry that have a very high demand for engineers now. So either one that you wanted to sort of specialize in, there's lots of opportunities. So I agree, you can hardly go wrong with either one.
My advice to students is usually to follow your passion, because if you're going to spend a ton of time working on something, make sure you're excited about it. So don't try to guess which one's going to pay you the most when you get done or anything like that. Just think about what you want to spend the most time studying.
Great advice from all three of you here. So a couple additional questions. And this one can be for anyone here to answer. Should I use a Mac or a PC for my coursework?
So I could take a start at that one. If you use a Mac for my course, you need to make sure that you have the x86 version currently. I'll be in the process this summer. Since I only teach part-time, I have limited time that I can do for course development, and this summers are kind of my course development time. So the containers that I use for auto grading today are limited to x86, and I'm going to fix that this summer. But for the time being, you do need to do an x86 version of Mac if you are using a Mac. There are also some information available in my course about how to use a cloud-based runner. So if you want to use a Mac system with some like a Google Cloud hosted runner, that's another option, but you will need some build system based on x86.
So for the FPGA specialization, all the tools are designed for use on a PC. None of them are supported for the Mac. And so using a Mac would be really problematic and it's not recommended. It is possible to get some of the work done on the Mac using a virtual machine and running the software tools in Windows as it runs on the Mac. Of course, that slows it down quite a bit. But when we get to the point where we have to interface to the development kits, it's very difficult to get that interface to work with the Mac. So to just avoid a lot of frustration in that particular class, you need to have a PC, I think. It's probably not true in a lot of the other classes, but in the FPGA specialization, a PC really is probably required.
Yeah, so I'll say I'm a Mac person, and Coursera works fine with Mac. No problems there. The issue is when you just get to these, a lot of these tools that often they don't work on Mac. The C programming, if you're doing Code Composer, it's fine on the Mac, which we do in the Power Electronics Lab course. The assignments using LT Spice, there's a Mac version of LT Spice, but it only has about half the features of the PC version. And so what I do as a Mac person is I do run an x86 Mac and I install Boot Camp on it, and then it runs fast, in native mode on the Mac. But if you have a newer M1 based Mac, then you can't do that.
Oh, thanks. Great insight and just some of those good tips that help our students be really successful when they're in their classes. Professor Erickson, I have another question here for you. Power electronic products like UPS solar UPS solar inverter are made with, hopefully I get all these acronyms here correctly. ASICs, FPGA, and DSP. Oh, okay. ASICs, yeah. FPGA, DSP, and high-end software. Will these things be covered in course?
Well, the development of, say, an FPGA controller or some ASIC controller is not something that we cover in a power electronics course. So, if you want to learn the FPGA programming, then I'd say go to Professor Scherr's course. And it is applicable to the power electronics as well. ASIC design. We offer analog IC design on campus, but today we haven't offered a course on that yet in the Coursera format.
Great, thanks. So Professor Scherr, then how much math and what math courses are needed to excel in FPGA?
So as it turns out, there's not a lot of math required in order to do work in FPGA. You need to know Boolean algebra in order to do some of the logic problems in the course. But other than that, we don't do anything that requires any calculus or anything like that. So, it's pretty approachable for pretty much anyone who's got a digital logic design background and knows Boolean algebra.
Great, thanks. So next one, back to Professor Erickson here. Do you use Simulink and MATLAB in power electronics? And also, do we get to design power electronics to the hardware level?
So yes and yes. There's basic LT spice simulation in the first course. In follow-on courses, there is MATLAB in that course. And we actually, I mean, if you're an admitted student, you have access to the campus site license software, which does include the full MATLAB package as a student. And then as far as hardware design, yes. So there are homework problems that have different aspects of that, but then this capstone design project course does do a full analog design and a full controller design.
Great, thank you. So back to Professor Scherr here. What's the reason behind using Quartus?
So Quartus is an FPGA design tool suite that includes a number of tools, including design entry tools where you can put in your Verilog or VHDL code, and it will compile that. So there's the compilation includes synthesis to map the logic to a particular FPGA architecture. And then there's also a place and route tool, which will route all the connections between the different logic cells inside the FPGA, and all that place and routing is done within Quartus. And then once you've created all the routing, you usually run a static timing analyzer on that to verify the design, and then it's ready to program the parts. So you actually program the FPGA from Quartus. So Quartus does all of the compilation, all of the programming, and a few other things in terms of modeling and so on. So it's a pretty complete tool that allows you to build circuits in FPGAs and even to write some software and run that inside of the FPGA.
Great, thanks so much. So for Professor Walkies, can you provide us a little more information about the study materials that are available to students in your courses?
Sure. So I think this varies probably quite a bit by courses. In my case, there are a few different books that my course is based off, but I've tried to make it so that the books are optional. And in one case, for the Linux kernel development specifically, that book is actually open source and publicly available. So really the main study materials are the slide decks that are associated with the lectures. And in a lot of cases, I'll reference in every slide deck where the material came from if you want to go back and read the book. And in some cases, I'm using material that isn't based on the book, but based on web references and things like user guides for the build tools that we use, that kind of thing. Those will also be referenced in the slides.
Great, thanks so much. So as we're getting here towards the end of our webinar today, I do want to pose one question back out to all of our panelists again. So as a wrap-up point, and I know we've touched on it a little bit earlier, but maybe if you have some words of encouragement or you want to tell us a little bit about your motivation to create your courses on Coursera and why you were interested in being a part of this program with us and having your material out on the platform.
I guess I can take that one first. I mean, I've been teaching various distance formats for 40 years, and I've seen the frustrations and difficulty that the distance students, who are working professionals have when they try to interface the traditional campus format. The campus format is just not as attuned to the needs of working professionals as it could be. And Coursera lets us offer all of our courses every 8 weeks. And makes them in small chunks that are much more manageable than taking the full-blown semester-long course. Also, I have to say, I taught power electronics as a free MOOC 10 years ago, a massive open online course. There were 45,000 students in it by the time the course was done, around the world, and the discussion forums cranked away round the clock, and it was just a totally amazing experience. So it made me a fan of Coursera. But you know, this isn't the same thing as that MOOC was, but still, it's it's really been a rebuilt format designed from the ground up to address what I think are the key pain points for working professionals, to be able to access these courses, make it near on demand or close to on demand, and be in a much more manageable format, and something where our limited number of faculty can still put up these courses and have them available, just have all the courses available all the time.
So I was excited to put a course up on Coursera, largely because I wanted to help people leverage the technology you find in an FPGA to build better products. And this is a way to kind of enable and empower people to be able to do more of that kind of work. I've taken classes on Coursera myself. I find them really useful. And I wish that I had this opportunity when I was a younger engineer to be able to get some of that extra training without a lot of effort, without having to pack up everything and go to a class and so on. And so, that was really attractive. And so I thought it'd be a way to be able to give people, a further opportunity to be able to learn how to use some of these devices.
Yeah, I'd echo a lot of the comments that were said previously, but I've taken some Coursera courses, and really some of the courses I've taken, after leaving them, I've been just thinking someone really needs to do this for embedded Linux. And so that's what I've tried to do with my course. And I love so building a course is an immense amount of work. I didn't have the understanding of it until I actually did it once myself. But if you go through all that work, you want it to reach as many people as possible. And so for me, that's what Coursera allows me to do. And that's why I'm excited about it.
All right, everyone, we have come to the end of this webinar, and I would like to thank Carly for being our reader. Thank you, Adam, for answering the Q&A. And of course, thank you for our presenters, Professor Bob Erickson, Professor Tim Scherr, and Professor Dan Wackes. If you have additional questions, please email us at msce-mooc@colorado.edu. Thank you again for joining. We will send a link to the recording next week, and have a great rest of your day.